Hello, everyone. It's nice to see many faces that I know. And for those that don't know me, my name is Stuhldreher. As the guy said, I'm a final year undergraduate student here at UCL. And today, obviously, I'm going to be talking about soft robotics. It's a field that I had the opportunity to work in during my third year project while I was being supervised by Dr. Helge Woerdeman. So I'm going to give you a bit of an introduction on soft robotics because it's not the sort of thing that you hear every day. So I'm going to talk about what they are and what the advantages are, and obviously I'm going to go a bit more into my project and what the future of the field is. Soft robots are being inspired by biological systems such as the elephant trunk or the octopus tentacles. And the main characteristic that these systems have is that they don't have any backbone or any rigid links, and this allows these animals to perform very dexterous movements and change their stiffness. For example, as we can see here in the elephant, for the octopus, it's able to move around objects with much ease and is able to squeeze through very narrow gaps. So researchers have seen this, and they realize there's a huge potential to be implemented into robotics if we take inspiration from this. And using this as an inspiration, they've created robots such as this one. This was created by my supervisor, Dr. Woerdeman, and it's a soft robot made out of silicon. It's actuated with pneumatics, and you can see that it moves in a very similar fashion to the biological systems that we saw before. It's able to move around. It has several sections, which gives it even more dexterity, and it's able to extend and retract. It's also very easy to get into miniaturization, so then it can be used for minimal invasive surgery. Now, the robot which I work with, it's a bit different. It's made out of fabric and a latex bladder, otherwise known as a balloon. And the way it works is essentially you have the latex bladder, and it's surrounded by a fabric sleeve. Now, what happens is that we put tendons on the fabric sleeve, and we pump air into the latex bladder. And this allows us to essentially control the stiffness of the robot while moving it around by pulling the tendons. So, as I said, for example, we can squeeze this through very narrow gaps, and then once it's passed, we're able to inflate it and perform any task we want. Then once we're done, we deflate it and we extract it. What I did for my project was work on the mathematical model of this robot to understand how it moves better. And with that mathematical model, I was able to create a control system to move it around, as you see now. And again, as the other robot I showed before from Dr. Woerdeman, it moves in a very similar way to an octopus tentacle. Depending on the tendons that I pull, it'll move to one side or the other, and depending on the pressure that I'm putting into as well, it'll be able to do different tasks that it has at hand. Now, the good thing about UCL and the MechEng department is that you have a lot of opportunity, and I had the great opportunity of showcasing my final product in the London Tech Week last summer, where I was interviewed by Tech TV. They came and they asked me about my robot. I showcased the system you can see there, and then the soft robot on the front. Basically what you see there is the aluminum plates are holding actuators that control the tendons, and it's also connected to a pump that controls the air that we're pushing in. Now, one of the people that came to interview me was a representative from the MechEng. And again, they asked me about my robot, and they thought it sounded really nice, and they decided to publish it in the MechEng press. Not only that, they also asked me about the future of soft robotics, and I'd like to close this talk with this because obviously that is the topic of the event. So, what are the future applications of soft robots? Where are these weird things? Where can they be used? So, I see three main fields. One of them being minimal invasive surgery, as I already said. Minimal invasive surgery, for those who don't know, essentially means that instead of opening up the body and tearing apart and working on the organs inside, you make a very small incision and you pass the tools through that incision, and that way you perform the surgery and you're not left with a 20 centimeter scar but a very small, tiny scar. So because these robots are able to squeeze through keyholes that we use on surgery, and the dexterity that they have allows them to move around organs with much more ease, then that means that they have a very huge application on this field. Another one is collaborative robots. The fact that they're soft means that they're inherently safe. So one of the big issues that we have nowadays with robotics is that how do we make robots work with humans while ensuring that the human will not be killed by the robot? Soft robots come perfect in hand for this, because if you get hit by a soft robot like mine, you pretty much won't get much damage. If you get hit by a piece of metal that weighs 30 kilograms, you're probably going to end up in the hospital with a nice scratch. So this has a huge impact. We can use it in manufacturing, for example, collaborative manufacturing, or assembly lines in which robots and humans in the future can work together. And the final one is autonomous cars, which we're going to get a very nice video coming soon, so stay tuned, from RoboRace. And in this, what we can do is we can work with haptics. Haptics is basically giving feedback to the user. And by using soft haptics, we can create, for example, driver seats that give feedback to the driver and assist him while the level of autonomy of his car is changing. So with that, I'd like to close it. As the name of the event says, the future is now, and I think that that future is robotic. Thank you very much.